Everybody, this is the last video of the continuation of thermodynamics. But so this I'm going to mostly dedicate to Carnot engine. But before that, I want to just touch upon something I couldn't cover in my previous videos when I talked about Gibbs free energy. Okay, so Gibbs free energy, as now you know, if I put enthalpy like that, entropy, and then in standard enthalpy, entropy, and Gibbs free energy. Okay. Now, in my Maxwell equations, I gave you something like this before. I'll put delta here, minus S delta T. Okay, so smaller ones would have been dg equals vdp, infinitesimal changes would have been like that. So at constant temperature, this entire thing becomes 0. So we can write delta G equals just V delta P. If it is a gas reaction from PV equals nRT, we can write V as nRT over P. So by replacing this V here, equals nRT dP, and then when you do the integration, you get delta G equals nRT ln. So this will have the final over initial. Now, what is this delta G means? It's the difference between the end result of G and the standard. It's nRT ln PF or PI. Okay, final initial. All right. So if I take this negative G to the other side, I get G equals G plus standard plus G standard plus nRT ln. We can write PF or PI. Okay, or we can right. Now let us take an equilibrium situation where I'll put just one reactant in the product, these are the stoichiometric values. Okay, so now if I'm writing the G for that, or delta G for this, it's given by G of products, or B minus G of A, right? So I put AB not to get confused with B's as product. This is the pressure, or partial pressures of the things. Okay. Right. Now, if I'm going to find the delta G on these ones, this G could be replaced for that, and the same thing for that, right? So I can write delta G equals, I write the whole thing. So GO for B plus let's write it here plus RT ln PB minus AGO for the A plus A of RT, because the stoichiometric value is the one we are putting in the front, ln PB. All right. Now I see these common terms. Okay, and I take the common because standard is together to a side. We can get delta G equals delta G plus RT ln PB OPA. Right, from the equilibrium, this is K equilibrium, right? Expressed in the terms of partial pressures. So I can also write it delta G equals delta G O plus RT ln K. But I can write it if it is in equilibrium, otherwise K could be replaced with Q, reaction quotient. Now, if Q equals K, that means it's in equilibrium. So remember that. So this is equation I wanted to explain to you. Okay. Now, at equilibrium, delta G is going to be 0. A reaction proceed only if the delta G value is negative, that you know. And if the delta S is positive, we did those calculations, right? So delta G is negative. So if this part becomes 0 at equilibrium, which is K equilibrium, you can use now instead of Q, then, so please go and check that when the Q is higher than K, and when the Q is lower than K, which way the reaction is going, right? So because product over A, so if product is high and A is low, then the Q value is high, means it has gone past equilibrium. Okay, so if the Q is low than K, the reaction is proceeding to the right. It's trying to get to that equilibrium level. Okay, so this is delta G is 0 at equilibrium. So we will get a situation like delta G plus RT ln K expressed in terms of gases. Then delta G, the standard, equals minus RT ln K equilibrium expressed in P over level. So we can use this as, remember this equation. Okay, so that's the equation I want to tell you. So when you're doing questions, when you watch one of my videos where I do some calculations, I'll be using this equation. Okay. Now we'll go for Carnot engine. So no engine can give 100% efficiency. Carnot engine could be the maximum efficiency you can get. The reason for developing is to show that we can compare when you're comparing other similar engines. Okay, and then when you're talking about it, if you're talking about a gas in a piston, always remember that we are always talking about PV work, pressure and volume work, but it's mostly we take it as PDV. Okay, inside piston, because the volume change we are talking about more than pressure change. But if it's an open system, which is like just there's something, then we can consider VDP, because the volume is more or less open, so that it is, the change is insignificant. Here the pressure is insignificant compared to 180 outside. Okay, so so we are talking about piston here, PDV work. Just want to check. So Carnot engine has 4 stages. So the stages go like that: pressure, volume. So we take the first stage here, and take the piston for the first stage. We have a gas, right? So the fixed molecules, we don't change n number. We will say that we are trying, the gas is doing some work and trying to expand. So if I draw it like this, now we have expanded, so the volume is higher. Okay, so but if we keep this high temperature surrounding is very high temperature, which we call it a reservoir, we make it isothermal situation. So the temperature doesn't change. Okay. So in this case, when we increase the volume, so here we'll say fixed point P1, V1, we'll get to somewhere here, which is P2, V2. The pressure is low, volume, because volume increases this way, pressure goes up that way, right? So if I draw line comes like that, because can you remember when we did gases, if you draw PV curve like that? Okay, so I'll go to that. Oh. Okay, like that. Okay, so this situation happens isothermal. Okay. Then so this is 1 to 2. So this is 1 to 2. Okay. Now from here we move it. Get like this. Now we do the expansion without changing the heat. Okay. Okay. So whenever the temperature is kept constant, this is the isothermal part, so it is going this way, and here the energy is going in. Okay, so if I take in this situation, okay, so one more thing I want to show is that if I take this is temperature, here the temperature is kept constant. So okay, so now the internal energy, when we keep the temperature constant, internal energy doesn't change, so it becomes 0. Okay, now when it is expanding, what happens is from this entire reservoir, the heat is going in. So when the heat is going in, of the work done on the system, or Q is positive. Okay, so can you remember this U equation? Q, depending on what you're doing. Now here, the gas is pushing. The gas is doing the work on the system is doing the work on the surroundings. Gas is doing the work on surroundings. So it's P minus W. But because it's isothermal situation, that U becomes 0. So now this equation is Q minus W. Now Q is positive because the heat is going in the first stage, right? Because it's in a big reservoir, so that's how we keep it anything. So when you got the heat, that molecules pushes this piston up. Okay, so this equation becomes Q equals W. So just remember that. Okay, so now we are going through the adiabatic process from, so let me put so we'll say A and B. Now then we are going to see what happens here is adiabatic. That means no heat change happens. Okay, so there's no heat going on in or out. This stage from B to C. Okay, let me erase this one so we don't have so unwanted things. But so this is isothermal, this is the adiabatic. I just write that. Okay. So in this case, the temperature changes. Okay, so the temperature changes. Now, when we go from B to C, which is adiabatic expansion, if I say this was kept with a TH hot, okay, and this is T1, we'll say. Now, in this adiabatic end, so TH, talking about the hot environment, it's going to T1, okay. Now, then the next is, now it went up now, okay. Ignore these ones. Well, you know, this isothermal situation. Now here, adiabatic situation. Now, this has gone further up, okay, because this is first is starting point, this is the start. From the start, it pushed up. Now, that was isothermal. Now here, from TH, whatever the temperature is coming, let's say 1. Again, it's expansion there, okay. It is called adiabatic expansion. First, isothermal expansion. This was isothermal expansion. That's why U was 0. Expansion. This is the adiabatic expansion. Okay. Then we are going the same way upward somewhere here. We'll say D. Now it is going to start compressing. So if I draw this one here, the starting point was here. Now we are pressing it and bringing down, and this point Q goes out. This is called, I put like this, isothermal compression. So here, the can you see the Q was going in? Now Q is going out. So heat is given out of the system. Out. Okay. This is also isothermal. Then isothermal, what happened? Delta U is 0, and work is done on the system, yeah, by the surroundings, and Q is going out. Okay, so be right for that isothermal one. Delta U is 0. Q is going out. Heat is given out. This becomes plus. So again, W becomes Q, but remember that Q is going out. Okay. Then from D to A, again we do the adiabatic compression again. So this time I can't show it at the same level. So we have compressed it again, but it is adiabatic compression. Okay. Now, so this is this bit. Okay. So you can see the 4 stages. So starting TH here, then TH here, then T1, then again T1 because this was isothermal part, then again T1 to TH. Okay. Okay, so that's the Carnot engine. Okay. When we do the adiabatic part, press there and then part, we'll say T1 and here T2. So in this scenario, understand that T2 is higher than T3. Okay, and it goes like that, it goes like that here. 3, 4, T1. So T1 and T2 are the same. T1 equals T2 because isothermic and it's high. Then T3 and T4 is same, but it's low. Okay. Now, so you understand. So we have two processes, two situations. First expansion, then compression. Okay, and the first step isothermal, then adiabatic. So then the compression also isothermal and adiabatic. All right. Now each stage we can write certain equations. You don't have to derive, but just remember this. Okay. So when I say process here, 1, 2, 3, 4. What is it? 1 to 2. Okay. So I put work. I'm just going to write the formulas for you to understand, and I'll start with Q. So that's U. Delta U and Q W enthalpy here too. Okay. So the first process is starting point. It's isothermal, right? So I'll just put it here, and then adiabatic. Then again isothermal. Then adiabatic. Okay. I'll give you the equations that we derive from this that you can use for questions, but I'm going to give you a set of here the equations. So the 1 and 2 are, that means expansion. And then this one compression. Okay. So delta U, you know that when it is isothermal, delta U 0. Then it should be 0 here too. Okay. Then if it is adiabatic, Q should be 0 because heat is not, and this one should be 0. Okay. Then what about work? This one just accept, because we don't want to, I don't want to derive at this stage. Okay. For general chemistry. So work is given by minus N R minus, why it's minus? Because the work is, when it is expanding, work is done by the system on the surroundings. nRT, and remember this is high temperature. Okay, ln V2 over V1. Okay, and then you know why the minus is nRT ln V2 over 1. Remember this temperature is high. Okay, then when you come the other way, when it is heat, the work is given by N CV capacity. T low is the final, which is the stage here. T1, T2 here. T3 from T1 and T2 are the same because it's isothermal. T3. So if I go here, adiabatic process. Okay. So when I say, remember this is high. Okay. So if I put small h, that's okay. Here, so N is low minus high. Okay, that's the work. Then when it is compressing, this is low ln V4 over V3. Okay. Then adiabatic situation, N capacity, they're all the same. T high, now that is the final one because you can see the last step from here we go up, right? T4 and T3 are the same. I have written all these things. Okay. Minus T low. So you don't have to derive, just remember these things. Okay. Okay, so put W for me. Now let me go to delta U. So delta U here is given by N CV T low So you can see this is similar to that because Q is 0, right? The equation is delta U equals Q minus W. Okay, that's how we get it. That's why. So then in this situation also, it should be N CV, but the difference is temperature. It's going to be high because that's the last one, minus low. All right. See, okay. Then when it comes to Q, when delta is equals, Q is equal to that amount, right? But in the opposite. So you can set N RT high ln 2 and then this one here also nRT, that's low ln V4 over V3. Okay, now when you just follow these ones, when you derive this V4 V3 or V4 turn it around, that's why this negative positive change. Okay, remember that. So just accept these numbers we have put it here because when you're deriving from the Carnot engine, we get a situation where V2 over V1 equals V3 over V4. Okay. So that situation we derive from these things. Okay. So delta H in the first one, situation 0. The second one, we'll say NCP, T low minus T high. And that's 0. So you can see delta U, delta H, and they're going to be 0, matching that. And then here, okay, you can see it has changed from U to that. So just accept these equations and remember them, and you can use them. Okay. Now, if you apply for the full cycle, when you go for the full cycle, what happens? It comes back to the same because U and H, enthalpy and internal energy, are state properties. So you just count from, if it goes all the way and come into the same thing, the full cycle, if we go for the full cycle, entire cycle, H is going to be 0, U is going to be 0. No, so U is 0. So U is going to be 0, H is going to be 0. Okay, because there's no change. It goes back, it's like a circle, you run and come back. The same thing, it's like a displacement. It's 0 if you run a circle. Okay, but Q, what happens? You add those things, right? You add them together. So for Q, it will be adding of these two. So I will write it like that. T hot, not a high, ln V2 over V1 plus n RT ln P3 V4 over V3. Okay. So this is V4, and then for work we just add these two systems, right, for the whole thing. So I can write the work as okay, right. So please remember these ones and remember when we are applying those things. Okay. Now, I'll show you one more diagram about same as PV. We can draw T and S diagram, that is with the entropy. So if you take the first, second, third, so this is the isothermal, and it goes this way, going in. It's the same things, not change. Then this is the adiabatic process. That way, then again isothermal, and then this process Q is going out. Okay, so of T high and T low, okay, the situations, and these are just the initial or the low at the low point, and then high point. In this case, if you go by the processes again, like I have delta T, delta S. Easier, we just have so 1, 2, 3, 4. Process 1, 2, 3, 4. Delta D is going to be 0 because it's the isothermal process first case, and this one is going to be NR ln V2 over 1. Okay, and the second one, the difference is just low over high, because low, it's not just low or high, it's final minus initial. That's why. Then entropy is 0. Then the third case, again, isothermal compression. So these are the same things. Okay, so here it's isothermal expansion, hepatic expansion, Q, and that is expansion. Then isothermal compression. So this is going to be 0 here, and this is going to be as you go, and here again minus NRLN, but here V4. Now, if I take the full cycle, all T and these are state functions, this becomes 0, that becomes 0, right? So remember that. So efficiency of a Carnot cycle, efficiency is given by this eta eta, given by network done by heat engine. Network done by engine, okay, divided by heat absorbed by the engine. Okay, it's the heat engine. Okay. Heat. So it's given by the work. So engine is a system, and Q. Hi. Okay. Now, if we what we learned earlier, we put all those things together. nRT, and then V2 over V1 plus nRT, and then V4 over V3. This is low here. ln V2. So when you combine those things, we get different formulas, but I'll write it here. T2 over T3 CV over R plus V3 over V2 T1 T4 CV over R equals V4 over V1 Remember when we did it, we said T1 because isothermal situation, T1 equals T2 and T4, right? Because isothermal situation. So therefore we get V2 over V1 equals V3 over V4. So no need to derive, just remember this one. Okay, so efficiency, ultimately we can final from what we wrote earlier. Efficiency is given by T high divided by T low minus T low divided by T high. Remember, so that's the efficiency formula. So remember this one, and remember that one. Okay. So with this information, so this is the efficiency TH minus TL TH and the volume. So the another one you have to remember is the work done in a Carnot engine. You can say QH minus QC, hot and cold, low and cold, or we can say cold here, L or C or low. Okay, that's one thing. And then remember these formulas, QC over QH. So I'm okay. So Q, H means the hot. So you can take as the starting one, H is 1, and cold is 2, because some books will have cold, hot and cold, someone will have T1 and T2. So T1 and T2 is an ideal way to check it, starting point final, but we'll say that it's going from hot to cold. Okay, so QC over QH given by TC over TH. That, then remember this one. And also efficiency. From this formula, that is this is the sign, this is the efficiency. You can give it as a percentage, first as a fraction, minus TC over TH. What I have done is I have just divide the whole thing. TH by DH is 1, TC over TH, that's what I get it. Okay, so this is as a fraction, and you can multiply by 100, and you can give as a percentage too if you multiply it by. Okay, so remember all this formula. Then let's see what else. Yeah, so V1 the first, it could be A, VB over VA, VC over VD, or 2 over 1, 3 1. So as long as you remember these one stages, then this formula, then you're okay with Carnot engine. All right, everybody. Thank you.